Hey guys, welcome back to Genius Learning. All right, in this video, I want to look at rotation. Physics 1. All right, the scenario, let's look here in the center. We have this brave physics professor standing on the center of this turntable. This thing spins around and he's holding his arms outward, holding weights, okay? And then he's rotating around a center axis in the middle. All right, he has set a rotating goal around the axis of 2 seconds in 1 revolution. Okay, so his moment of inertia, including the turntable, but not including the dumbbells. So blah blah blah. Let me break it down differently here. So we have the professor here holding his arms out, and you might have seen these type of examples for ice skaters or ballerinas. When they have their hands out and they're performing the spin, they pull their arms in and they start spinning faster. And so we're going to look at the conservation of angular momentum and how that helps ice skaters and this brave professor here spin faster once he moves the weights in and slower when he moves the weights out. So let's get started. Okay, so the first question. Okay, so the first question here is going to be, well, the first setup, everything here was given. So here we have this cylinder represents the professor. I just didn't want to keep drawing it. All right, and so this right here is the professor with his arms sticking out. Okay, so these are his arms, and he doesn't have weights in his hands in this scenario. All right, so these circles just indicate that he doesn't have any weights. And so what that does is allow us to measure the professor just by himself spinning with some omega without weights. All right, in this scenario here, now he's pulled his hands inward, right, and he's still spinning, and now his moment of inertia is 2.2 kilograms per meter squared. Times meter squared. His initial moment of inertia was 3 kilograms meter squared. All right, and if you're not familiar with what the moment of inertia means, because I know it's a little weird and everyone says it, but just to think about it in a kind of like a faster way. If you have your arms out, right, and you're spinning through space, then you have a lot of surface area, more surface area to slow you down. And so you will have a higher moment of inertia, right? You will have a higher amount of pushing things through the air the bigger you are, or the more like you stick out, right? If you make yourself really thin and just occupy a small amount of space where there's not a lot of traffic going on with your body and the particles around you, then you'll have a lower moment of inertia. So a higher moment of inertia means you just have a lot of stuff that you're pushing out of the way. You consume a lot of space. And then a lower moment of inertia means you occupy a smaller amount of space, or you push less through space as you spin. All right, something like that. So you just gotta like visualize it like that. And here we go. Hands are in without dumbbells. So this side here is without dumbbells. He's spinning, he has his arms out, and here he has his arms in. Okay, and what was given is that the moment of inertia started like this with his arms out, and now the moment of inertia has gone down as he put his arms in. And I'll show you why this makes sense. Okay, and then on this side here, he has dumbbells in his hands, shown by this thing that looks like an eye. They're 5 kilograms each. They're a meter away. Okay, they're 1 meter away from the center of axis. All right, and this is the Z. So this one is arms out with the dumbbells. Okay, and it's spinning, and then this one is arms in with the dumbbells. These look like little cylindrical men. This is funny. Okay, boom, there. All right, and this is 0.2 meters from the center of axis. So now that he's pulled his arms in, it's not really all the way to the center, you know, of the z-axis, like all the way to, they just pull him in really close to his chest, and they're like 0.2 meters away now. So before they were 1, now they're 0.2 meters away. And then that's it. And then they tell you this, that 1 revolution in 2 seconds. That's how fast these are spinning right here. So this one's spinning, it has this mass sticking out at 1 meter, and it tells you 1 revolution in 2 seconds, aka t is equal to 2 seconds. So this is period, the t, the amount of time it takes to cover 1 revolution. All right, so we have everything. Some definitions. This is angular velocity, how fast you're moving in an angular direction. L is the angular momentum, and we'll speak about that now. The moment of inertia, and Ke is the kinetic energy of rotation. Okay, here's some formulas. This is for the angular velocity. Here we have angular momentum, kinetic energy for rotation, and the moment of inertia, mr squared. Okay, so our first question. Let's find the moment of inertia of the professor plus dumbbells when arms are out. All right, this is a little tricky because you might think, oh, you know, I can just go to this one where it's the professor himself and the dumbbells are already on him. But that's not the case, because you have to consider his moment of inertia by himself, and then you have to consider the moment of inertia of these two weights independent of him. So they're also moving through space, and he is they're spinning through space. And so they need to be taken into account separately. And so what I mean is, we're gonna do I, and this is gonna be a lot of labeling, so I kind of just I don't wanna label too much, but I will. I just kind of want to talk about it in the beginning, and you just have to know which one I'm talking about, and I'll make it clear, but just know that there's going to be a lot of labeling for this one. So, moment of inertia of the professor and the dumbbells. So, moment of inertia, I'm going to put total, right? T for total, and I'll just write it out. Total, and then dumbbell out. See, this is a lot. Okay, so I'm not gonna write that every time, but this is the I that we're talking about. This is the total dumbbell out. What that includes or needs to include is the dumbbells here. All right, so we already know. So let's start off with this one. Okay, so we need 2 things. We need the professor and the dumbbells. We already have here the moment of inertia for the professor with his arms out empty. So that's good. We have 3 kilograms meter squared. This was already given, right? Then we need the professor, but with the weights. So we're only focusing now on the weights because we already have him here with his arms out empty. Now we're focused on him with the weights. So here, let's put in these values, and so we're going to do plus, and since we have 2 of them, we're going to consider mr squared plus mr squared. All right, each one of them needs to take up their own moment of inertia term. Okay, box this up here, and so let's fill these out. So this is going to be 5 kilograms for the mass. And then we have 1 meter for the radius, right? Because the radius is from the axis out, plus 5 kilograms and 1 meter radius. And we still have this 3 kilograms and equals I total dumbbell out, something like that. Oh, it's horrible. Okay, so we have all of this, and this is 1, these are 5, so that's 10, and then that's 3, 13. So I total dumbbell out is going to be 3 plus that, so 13 kilograms meter squared. All right, so this is the moment of inertia of the professor plus the dumbbells when the arms are out. All right, so we got this one done. Let's box that up. And then now let's do the next one. Okay, we got B says to find the angular momentum. Angular momentum of the professor plus the dumbbells. Okay, when his arms are stretched out. So dumbbells when arms are out. Okay, so we have our next one, and usually you'll see that it's an easier pattern to find the moment of inertia and then find the angular momentum. Okay, so we got the professor plus the dumbbell. So what does that mean? We need both. We need both him without the dumbbells and then with the dumbbells by itself. So let's take a look. So the angular momentum of the professor plus the dumbbells when the arms are out. So for over here, I left these two boxes empty. Here we have the dumbbells and his arms are out. And so let's do something first, okay? Angular momentum. If you were to see this problem and you see that, write down the formula. So you have L is equal to I omega, right? And so you have that formula. And what do you see that you're missing? Well, I know that I have to calculate this one because this is the professor with the dumbbells, right? And his arms are out. And this one is the professor with his arms out, but no weights. Okay, so that's what we're looking for here. The omega here is the same as the omega here. We know the moment of inertia of both of these, right? We know the moment of inertia here, and we found the moment of inertia here, okay, to be 10 because it's a combination of both of these. Okay, so moment of inertia for one weight and moment of inertia for the other weight, and so that's 10. So we have the I, and now we need the omega. So let's find the omega. We're going to use our formula here for omega, and they told us here that t was equal to 2 seconds. So omega is equal to 2 pi over 2 seconds. 2's cancel out, right? And then we have omega equals pi. Pi is equal to 3.14, and it's going to be rads per second. So radians per second. So that's what omega equals. Okay, so we have our omega now, and we have our moment of inertia. Now let's try to calculate the angular momentum for both of those parts. So we're gonna need, let's do angular momentum total. And again, I'll put, you see there's a lot of labeling, but I'm gonna put angular momentum total, which is made up of the angular momentum of the professor without any dumbbells and his arms are out. Okay, so L, and we'll call it without the dumbbells. Okay, and then plus the angular momentum, right, with the dumbbells. So we'll just say with the dumbbells. I guess that's easier. All right, so this is what we're looking for. All right, and to get that, let me see if I could move this up a little bit. kind of lose the professor there, but we'll get him back in a little bit. All right, so let's erase some of this. Okay, so this is what we're looking for. The total angular momentum, which is made up of the angular momentum of him without the weights, arms out. Angular momentum of him with the weights, arms out. Let's look for this one, okay? We got L is equal to, or L with, what did I say that was? Without? Oh yeah, okay, without. See, so I don't like all this labeling. All right, so without. So what is our formula for angular momentum? We got I. So what is the I here? It's already given. So we got 3 kilograms meter squared. Perfect. Now, omega. Uh-oh, what do we do? We already have it because here, this omega was corresponding to the arms out. So we already have the omega for both. These are rads per second. Okay, and let's see, right, because this part is already done, and let's total that up. We're gonna have angular momentum of just the professor without the weights is gonna be 9.42 kilograms meters squared over seconds. Okay, so let's hold that for a second. Let's make sure you guys can still see me here. Okay, and then we got the angular momentum of the, with the dumbbells. I just forgot what the hell the W was for. All right, so angular momentum with the dumbbells, which is this one here. All right, what is the moment of inertia? Well, we calculated that here. This is the moment of inertia. Sorry, this includes him without the weights. So it's only these two. Okay, so the moment of inertia for this part here is going to be a combination of mr squared plus mr squared, which is this. And we're going to put this right here. And that's 10 kilograms per meter squared, or times meter squared. And then the omega is the same thing, because in that revolution, we were told that it happened in 2 seconds. Okay, so that holds true for the entire thing. All right, and so multiplying these together, we get 31.4 kilograms meter squared over seconds. Perfect. Now we just add them up. So these are the two that we needed, and adding them both up, let's label that L total, right, for his arms out, and adding them up, we're going to get 40.82 kilograms per meter squared over seconds for the angular momentum total. All right, so let's, perfect. That's for part B. All right. Okay, so now let's look at part C. Now let's try to bring the professor back. All right, cool. So let's do part C. Make sure we got room over here. All right, so what are we looking? Find the moment of inertia of the professor plus the dumbbells when the arms are in. All right, so now we're dealing with when he has his arms in. So find I. So just like we did here, we have to add up the I's, the ones where he has his hands in, but he has them empty, and then where he has his hands in, but he has the weights. So again, we'll say, what did I put there? Okay, so I total of dumbbells in. So I put here total total dumbbells out, total dumbbells in. is equal to the moment of inertia here, which was already given. So 2.2 kilograms meter squared. This is a 2, this is a point. Okay, then plus, and we need the moment of inertia of both of these. So what are we gonna have? M let's see. Okay, I think no, we didn't calculate that. Give me 1 second. Sorry about that. I want to go in order here. So let's see. Okay. All right, here we go. So we need to calculate it just like we did for here, right? We have the total, and we were given one of them, the first one, the one where he's without the weights. And then these two come about because now we're dealing with the weights, but in this situation for this question, we're dealing with the weights. We have the radius and we have the mass. So plus m r squared plus m r squared, just like the other one, right? And then let's do I total dumbbells in. And let's do, we're gonna rewrite 2.2 kilograms meter squared plus, I'm gonna combine, so the masses are the same, right? It's 5 kilograms. So I'm gonna pull the mass out, right? 5 plus 5, I'm not gonna write kilograms. And then the R's are together. So I'm gonna put 0.20 squared. That's 0.2, right? Squared for the R. So this comes out to be 0.4 kilograms meters squared. Okay, just this part. And just this part is the moment of inertia that we were looking for in order to add it to this to get the total. So we got that plus the original, which is him without the weights and inside. Moment of inertia, total dumbbell in. Oh, it's terrible. All right, so calculate. And what do we get? Okay, I did put it in the calculator. So we got 2.6. So, man, I'm gonna put the answer over here. I total dumbbell, what was the I for? Inside is equal to 2.6 kilograms meter squared. All right, so for lack of space, I just put it over here. And then all of this was just for part C. All right, we calculated the moment of inertia of the professor plus the dumbbells. All right, so remember you gotta do that separate. You got him here without it, and then the two dumbbells here separate. Okay, we have that total. Now let's go for question D. Okay, we have now find, just like this one, we gotta find the angular velocity. So find the angular velocity, angular momentum. Whoops. So angular momentum of the professor plus the dumbbells. When his arms are in. Because remember, now we're dealing with his arms in on this side. Arms in, arms in. All right, so let's do that. So similar to this one here, we got our formula, right? We have, let's see, we have angular momentum, right, which is I omega. But for this problem, we can now use the conservation of momentum, angular momentum. All right, and I'm gonna explain exactly what that is and how we use it and give some other details about it because it's actually pretty cool. All right, so let's move this up. Again, we'll lose the professor. And the conservation of angular momentum, let's write it with pink. We're gonna do some, it's just like conservation of energy or anything else. The angular momentum in the final, right, is equal to the angular momentum initially. And again, I'm gonna explain exactly what that means in a second. So what do we have already? We already know the angular momentum when his arms are out, right? And so his arms are out in the initial state, right? Initially. So let's put this number here, because then finally he's gonna put his arms in, and then that's when we're gonna say that he did the second thing. So initially he started off with his arms out. So this is the angular momentum. Okay, kilograms meters squared over seconds equals, and now for the final angular momentum, now he put his hands in with the weights, right? And we're trying to calculate how fast this omega is going now. Okay, so now we're gonna leave it on this side, right? We're gonna do I omega, right? Just because that's what the formula is. And this omega corresponds to this one, like the final omega, as a result of opening it and now closing it. How much faster did we go? So this I right here is, let me see, total pulled in, which we just calculated right here. All right, so just like the other one, it was sequential. We got this I is the total I with the dumbbells in. You see all the notation you need to do, because it's not just any I. You have to know which exact one you're looking for here. All right, and so the angular momentum final, you need the total of him pulling his arms in. Now we're good with that one. And we know this number. We don't know that, and that's what we're looking for. So let's solve for omega. So solving for omega, we're gonna get, let me do it over here. Omega is gonna be, I'm gonna put this underneath all of this. So I'm gonna have 40.82 kilograms meters squared over seconds. Everything over 2.6 kilograms meters squared. All right, so really I'm just doing 40.82 divided by 2.6, and then all the units, they cancel out. You should know what the units are going to be for angular velocity. All right, so then we're going to get angular velocity is equal to 15.7, okay, rads per second. All right, so now let's talk about what this means. What does all this mean? All right, so let me get another color. All right, blue. All right, I'll just do this. Okay, so let's see what happened here. We went from having, this is gonna be the professor without the weights. This is him with the weights, okay? So the whole time the professor has the weights in his hand. So we're just measuring the moment of inertia and all his things without it, and then with the weights separately. So when I say without it, he physically doesn't drop the weights. He always has them in his hands. So we have here, right, that omega that we found, which is here, is 3.14 rads per second, right? We found it to be pi. We used this formula, and it told us that it made 1 revolution in 2 seconds. So from that, we found this omega. Okay, that's with his arms out. Now, when he puts his arms in, look at the omega that we find. We find that he's going 15.7 rads per second. He's increased his speed. All right, and so I'm gonna explain why that is and what that means. Okay, so I don't want to change papers. Can we still see the professor? I'm just gonna grab another paper here and do it on the side. Right. Let me see. I'll put it here. All right, so let's look at what happened here. Okay, we got omega is 3.14. Let's look at omega initial, we'll call it, okay, is equal to 3.14 rads per second. And then omega final is 15.7 rads per second. Okay, so he had his hands out and he's spinning. He made one revolution and we found that he's going 3.14 rads per second. Okay, cool. Now he pulls his hands in with the weights, right? And now he does a revolution, he's going 15.7 rads per second. So he increases speed. And this is the reason why. So we have conservation of angular momentum, right? And angular momentum is this formula right here. What does conservation of angular momentum even mean? It means that these two numbers here cannot change, all right? So these do not change. And what that means is that physically the numbers can change, but the overall value on this side cannot change. So for example, if I have if I have the moment of inertia for an initial movement or whatever is I don't want to put a number to it. Let's say 3 kilograms meter squared. And then I put on a jacket or I put on something that makes my moment of inertia heavier. And so I've increased now my moment of inertia to, let me keep it as 1. So let's say 6, right? 6 meters per second, whatever. So I'm just showing that I put something on that increased my moment of inertia while I was spinning. And I'm gonna show you what happens here and why it's called no change. Because if I increase my moment of inertia, then my omega has to decrease by the same amount to preserve no change on this side. So if I increase by, or if I double it, let's say I double my moment of inertia, then I'm gonna half my angular velocity. So if these were numbers, let's say this was 3 and this was 6, you know, or like 12, it doesn't matter. So let's say L was equal to 3 and this is equal to 12, right? This represents I, this represents omega. So conceptually, this is for you to understand. If I increase, or let's say I do it with my my omega. Let's say I slow down. I'm spinning, right? This represents spin. I'm spinning at 12 rads per second, and I slow down to half my speed. So now the omega has gone down, right, by half. So it goes down to 6, right? Now it's 6. So the I has to increase by a double, you know, because this was halved. So let's represent it as you halved the omega, and so the moment of inertia now you have to double. All right, so basically anything that you do to one, you have to do the opposite to the other. This side cannot change. It doesn't matter if this person has 40 and this person has 20, or this person has 40 and this person has 20, or if he decides to go to 30 and this side has to get to 30 also. Yeah, I mean, whatever happens on one, the other one has to compensate and preserve the conservation of energy. I mean, the conservation of momentum. So that's what it means to say the conservation of momentum, that there's no change on this side of the equation, meaning when one changes, the other one will compensate. And, hey, nothing to see here, except there is, we see an increase in speed. Then what do you think happens to the moment of inertia? All right, so let's take a look. All right, if I here, right, now understanding that a little better, let's take a look at this. We got the moment of inertia, the omega increased. Let's see what that looks like. Let's put our conservation of momentum equation. We have I omega. So what happened here was that this increased. Okay, so omega increased in speed. What needs to happen to the I? That the moment of inertia needs to decrease. And that makes sense because remember I told you the moment of inertia is how much you're dragging around, like your resistance to movement because of, how much space you occupy. You have like something really flat and big, then you're gonna, hit more things along the way, slowing you down. If I decrease all that, if I make myself pencil thin and I make myself, fly through the air very subtle without hitting things, then I'm gonna go faster. That's why my omega is going up. So if I decrease the amount of things that I push in the air and the amount of space I occupy, then obviously I'm gonna go faster. All right, and so we can tell from this answer that the moment of inertia has decreased, meaning they have put themselves in a tighter position and occupy less space or less like limbs, less junk in space spinning. And we can find all that just from understanding one value initially and what happened to it after. All right, and so now the same thing is going to occur for kinetic energy. So kinetic energy, let's do that. All right, and so I saved this little spots here for the kinetic energy. So let's do, let me see, where did I put it? Okay, here. We need so we want to compare the kinetic energy final to the kinetic energy initial. What happens? What do you think happens when you put the weights in, you start going faster, right? What happens to the kinetic energy? And so we have the kinetic energy is equal to 1/2 I omega squared. We know I is mr, so let's write kinetic energy is equal to 1/2 mr squared, right? And we know that omega, right, for this 2-second period, whatever, we found to be pi. So I'm going to put pi squared. And we can leave it like that because what we need to see is not the actual value, but which we can get because we have all the numbers, but you'll see exactly what I mean in a second. So this is the kinetic energy for your arms out. And now when you put your arms in, right, let's do the kinetic energy. We got kinetic energy is equal to 1/2 mr squared. And now for the omega, we have a new omega that's higher. So we have 15.7 squared. All right, so you see why we don't even need to calculate the numbers because this is 3.14 squared. This is 15.7 squared. This is going to be a higher number when we calculate it out. So let's just make sure of that. Because this R we have 0.2, so 0.2 squared, right? Then we got times 5 times, we have 15.7 squared, and everything divided by 2. So 24, okay, this is going to be roughly 24.6. That's for energy, so energy units. And here we're going to have 5 times, in parentheses, this R is different, so this R is 1. We're going to have 1 squared, which is the same thing. 3.14, so 5 times 3.14 squared, and everything there divided by 2. So constant, you see? We got preserving the energy conservation and angular momentum. All right, so because we chose specific radiuses, right, these two kinetic energies are conserved. So we're not losing energy, because what's happening is as we are going in, right, and we're losing one value, we're increasing the spin, so the omega, compensating for what we lost. And here, since we're slowing down because we're now extending ourselves, we are transferring the energy from spinning fast to slowing down, and a lot of that energy is transferred through chemical energy. And you know, we're not going to go into that, but the real reason that, you know, you can transfer the energy from omega, like a spinning, to your chemical self is because when you're holding out, let's say this is you, when you're holding the weight out here and you're spinning, you have centripetal forces, right, that are making this thing want to go in when you're spinning, and centrifugal forces that are going out that make you want to let it go and just, you know, naturally let go of something. If you're spinning fast, these things are getting heavier and they're pushing in one way, they're pushing out another, but depending on how fast you're going, one of these forces is going to take over. And so when it does, the chemical energy in your arm needs to be able to hold it, right? And then when you're pulling inward, you need to do work in order to bring that weight in here, as centrifugal forces are wanting to push it out. You literally have to do work to bring it in, and that energy is what is transferred into this omega, and vice versa. When you slow down, it's because you let go and the arm just, you know, it kind of swung out because it wanted to compensate for the loss in omega. Okay, so we covered a lot, but I think the process is the moment of inertia. We got angular momentum, okay, and now we know how to understand them and what the conservation of energy means, that this side does not change. If they tell you, you know, in a question, what happens if I triple the final angular velocity, right? They tell you, hey, if you triple the angular velocity at the end, what happens to the moment of inertia? Well, this has to go down by 1/3. That's it. So it just happens, it's going to be opposite, all right? And that's fine. Kinetic energy, you need to see if before and after is going to be the same, or you can lose some, you know, this goes all the way to 0, or if this gets really, really close, then different things start happening. But yeah, this problem was a little bit in depth, so I hope it helped out. All right, thank you guys. Comment below if you guys want to see other types of videos on the same subject. All right.